Welcome to section 4 of this chapter. We are going to talk briefly about the different kind of orbitals that you'll find in atoms. So this is talking about basically the shapes that electron clouds can make. Okay, and this is all based on probability. We don't actually have images of electrons or anything in these orbitals, but okay, so in the modern atomic theory, which we talked about back in 4.1, electrons can be found only in certain energy levels. Okay, so good way of thinking of that is kind of like the energy levels in a house, okay, or in any building, basically the floors, okay? You're not going to find electrons between levels. That would mean that the electron would be in the middle of the floor, so halfway through the floor. That would be bad. Okay, so the location of electrons cannot be precisely predicted, which is why all of this is based on probability. There have been some indications that just by observing the electrons as they move around the nucleus of an atom actually changes the behavior of those electrons. So obviously pretty much impossible to actually study in their natural environment because just studying it changes it. Okay, couple things to point out here. Basically your first energy level is the closest to the nucleus, in this case the ground. Okay, and as you go up, each level gets smaller. Okay, each energy level gets smaller. Okay, so the largest gap in energy is going to be between the first and second levels. Okay, and then that steadily decreases as you continuously go up levels. So this is actually a really good model to kind of show that, because they do show the floor shrinking down as you go further and further up. All right, so electrons are really funky. They act as both a wave and a particle. Okay, so particle meaning that they are mass, they are matter. Okay, and then wave is generally referred to just as energy. Okay, so this is actually very similar to the way that light works. Okay, light also behaves as both a wave and a particle. Basically has matter, but is also energy at the same time. So it's kind of difficult to understand. It's really weird when you get down into the nitty-gritty of it. But so the orbitals, like I've been saying, in the electron cloud are based on probability of finding an electron there. And so due to like all of these probability calculations, they have actually discovered that the orbitals come in a specific set of shapes. Okay, so the number of energy levels filled depends on the number of electrons. So each individual orbital can hold 2 electrons. Okay, so each orientation of an orbital holds a max of 2 electrons. But you do have what's known as the octet rule. So an atom is happiest, stablest, most unreactive when it has 8 electrons in every orbital. Okay, in its outer orbital is the most important one. The outer orbital is the most important. The first orbital, okay, is actually happiest, most stable with just 2 electrons. And we'll see why in just a little bit. Okay, so as you go up, okay, you're going to have 2 electrons in your first energy level. You're going to add on, or it will go up to 8 in the next, okay, and so on and so forth, right? So, yeah, this will, yeah, don't worry too much about this just yet. So your outer orbital, your outermost orbital will have the octet rule apply, okay, where it becomes the most unreactive when it has 8 electrons in that orbital. Okay, that's why the noble gases are relatively unreactive. Okay, it's because they already have those 8 electrons in their valence orbitals. So, valence electrons are the electrons in the outermost orbital of an atom. So the valence electrons determine the chemical properties of an atom. They're the ones that are kind of just hanging out on the outside of the atom. So they're the ones that can react the easiest. So if an atom has one valence electron, okay, it wants to get to 8. Okay, so it's got, its outer orbital level just has one electron in it. Okay, so it could either try to gain 7 more electrons, or it could just toss out that one electron and go down to its next orbital, okay, the one that's second furthest out from the nucleus, right? And that would already have its complete orbital, okay? And so if an atom has one valence electron, it's easier to give up the one electron than it is to gain 7 more. So this atom's chemical properties really are determined by its ability to lose that valence electron, okay, and the ease in which it can lose that electron. So electrons will fill the lower energy orbitals first before going into the higher energy outer orbitals. Okay, so you're going to get full inner orbitals before you add anything into outer orbitals. So there are 4 different types of orbitals, and they are very creatively named S, P, D, and F. So except for the first 4 elements, every element has at least 2 types of orbitals. The first 4 only have s orbitals. So, s orbitals. These are the orbitals with the least energy in every energy level. Okay, they only have one possible orientation. They are spherical. Okay, so they can only hold up to 2 electrons. So when I talked about the first energy level only holds 2 electrons, this is what I was talking about. Okay, it only has one orientation, one basically way for the electrons to be in that shape. Okay, so it can only hold up to 2 electrons. Then 2 of the 8 valence electrons will actually be found in this orbital. Moving along, we have our p orbitals. So p orbitals have the second least amount of energy in every energy level. They have 3 possible orientations, so we're stepping it up here. They are what's known as dumbbell shaped. Okay. So you can see that the 3 orientations lay out on the x, y, and z axes. Okay, hence the 3 different orientations. Each orientation holds up to 2 electrons, so probability-wise, you'll have 1 electron in this lobe of the dumbbell and 1 in this lobe of the dumbbell. Okay, so you can hold up to 6 electrons in the p orbital. So 6 of the 8 valence electrons can be found in these orbitals. Alright, so now we step up to the d and the f orbitals. So these have the highest energy. D orbitals have 5 different orientations and can hold up to 10 electrons. So you'll notice this is where it gets real funky. Okay, the first 4 orientations aren't necessarily all that strange, but once you get to the 5th one, you have kind of a dumbbell shape and then a ring around the middle. Okay, again, all of this is based on probability of finding an electron in a specific region. F orbitals get even funkier. Okay, they have 7 different orientations and can hold up to 14 electrons. So, yeah, that's crazy. Okay, so just be aware of the d and the f orbitals and their shapes. Okay, you do need to know how many electrons the d orbitals can contain entirely. Okay, so all 10 electrons, and how many electrons the f orbitals can contain max, which is 14. Okay, so electrons can actually jump between energy levels. So if they want to jump to a higher energy level, they have to absorb energy, which will excite the electron so it can actually jump up to that higher energy level. But then once it gets there, it kind of regrets that decision and wants to jump back down to where it was. So it has to release that energy in order to jump back down to the lower energy level, what's known as its ground state. Okay, so that's where it started, so it's its ground state. The energy that is either absorbed or released can actually be absorbed or released in the form of a photon. So it's a particle of light. Now, if it's absorbed, okay, that photon has a very specific energy. Okay, so not everything will actually be able to absorb, not every electron will be able to absorb every photon. Because if you remember back from when I showed you that diagram with the different floors, okay, you can't go in between energy levels. And each energy level has a very specific amount of energy that you have to be in that energy level. So if the photon that you're trying to absorb would get you into an intermediate energy level, so you'd be between the energy levels, you can't absorb it. Okay? So when you release energy, okay, you can release it in the form of a photon, and again, it's going to be a very specific energy because you're losing a very specific amount of energy to jump from the higher state down to the lower state. Okay, now when you talk about light, the energy in light actually directly relates to the color of the light. So depending on the amount of energy that is released in the form of that photon, you're going to get a very specific color of light. So if you remember back several chapters ago when we had the extra credit video on fireworks, that's actually how they produce the different colors. Okay, all of the energy in the explosion is creating a whole ton of excited electrons, which then once they get up to that higher energy level, in the midst of that explosion, they immediately regret that decision. It was a bad idea. They want to jump back down, so they have to get rid of that energy. Okay, and they release it in the form of light and also heat, but yeah, hopefully they're not standing close enough to a firework to know that. Okay? So the energy of each photon is unique and determines the wavelength or color of the light produced. Okay, and that is it for this chapter.